Hello, my name is Louis Shower, and I'll be going over the Physics 2211 Lab 2 Projectile Motion presentation. So first I'll go over some models and principles. We're looking at projectile motion, which is free fall with only gravity acting upon an object. You see some asterisks there, because we're also examining drag force, which is a force acting upon a moving object, which is in the opposite direction of the motion and is proportional to velocity squared times a constant b. Some principles that we're also looking at is Newton's first and second laws, which includes the momentum principle, that's the second law. And then for our modeling, we're going to use GlowScript and Tracker Online. So Tracker Online is to track the thrown projectile, which in my case is a paper ball crumpled up, and GlowScript Online to create an online physics model, both with and without drag. And then we use these tools to create an accurate model of a thrown paper ball with and without drag. So here I have some results. I have the position for both X and Y from Tracker in the top left corner. I have a video in the bottom. Hopefully that plays. My bad. And we found that the object is able to gain more speed without drag, obviously. And we found that X velocity remains constant in projectile motion, which is consistent with Newton's first and second laws, which we looked at last week as well. And then here's just some graphs from my results. So you can take a look at those. Then here's the physics equations and ideas. We have, this is the momentum principle in the top left corner. That F net is equal to change in momentum over change in time, or change in time, delta t. And then I just have some pictures for gravity and drag. So you can see that the ball is accelerating downwards. It's accelerating downwards and the motion is downwards, which means that the drag will be upwards because it counteracts. So Newton's momentum principle tells us that net force is equal to change in momentum over change in time. We have force and gravity accelerates downward with constant F of g equals mg. We have the drag force, which is the opposite direction of the motion, pulls back with the force of drag equals negative b velocity squared. And that we're assuming that there's no motion in the z direction, just like as an assumption. Okay, and now we'll go over some calculations and preparations for the GlowScript model. And I just got to mention that the system is a paper ball, crumpled up paper ball. So our ball's initial position is 0, 0.250, which is provided by Tracker using the coordinate system. Our ball's initial velocity is 1.1, 2.029, and 0, again, because we're throwing it to no z velocity. And I found that using v2 minus v1 over delta t. And those are just the numbers I did. You can check my math if you want to, or you don't have to either. Delta t is 0.033, which is provided by Tracker. That's just how it automatically divides the time. And then our b value, which is for our drag coefficient. We got that. I did that like experimentally with GlowScript. I messed around until I got it. But okay, now here's the rest of my code. I figured I'd show you this just to make sure you can see all of it. Probably looks very similar to your code. I don't really have too much to comment on this. Here's some comparisons, analysis, limitations. So you can see that my model without drag, the final position in the x direction is very consistent across all three, which is very good because the velocity is constant. So I hope that's true. It's pretty close. I think that's pretty close at least. The final position also looks pretty good between the model with drag and real life, because I modeled the drag around real life. But the model without drag is very different, which shows the air resistance is a significant force. But the final velocity in the y direction, there's a little bit of a disparity between the three. And some of that could be because of camera lensing, movement of the camera, ball shape, air movement, etc. Or it could just be a calculation error by me, but you don't have to look too deep into that. But other than that, the shape of the graphs between the three models is pretty consistent, which shows that I think it was a pretty good model, which I'll show you on this next slide here. There we go, and I'm comparing the y position in meters versus time for each graph, just because that's a graph that each website gives me. And then for some of these extension questions, let's see here. Do any of your models predict the terminal velocity? If the answer is no, what similar experiment could you? I said no, none of the results I found showed that there would be a slowdown to the terminal velocity, because the velocity is consistently increasing in the y direction. But by tracking the ball as it fell from a much higher position, we may be able to see this take effect. And the second question, if the ball were thrown straight up, would the time to fall have changed? No, y velocity is not at all contingent upon x velocity, so it would take the same amount of time And then here's a computation of my answer that I use GlowScript for this. Thank you for listening to my presentation. I hope you liked it.